All right, welcome back, everybody. This is William M. Briggs. We're continuing our lessons in uncertainty, probability theory, the logic of science. I hope hagfish out there will forgive me. I don't have a jacket on. It's very hot here today in the shack, so I went without. There's no air conditioning out here, so we have to have only the breeze. Also, thanks to Paul for this fancy Korean chalk. Greg Glassman gave me a box of this earlier, and I expended all of it. And now I have a brand new box of this stuff, which writes a lot cleaner. It comes off a lot cleaner, so it saves me some time to erase and everything. All right, let's talk about binomial sins. We're going to be doing something extremely important today. Let's talk about what we did last week, and then we'll sort of wrap up where we are to this point. Because we're at the second point. There was only really 2 points so far, at which everything starts to go horribly wrong in ordinary courses, in ordinary thinking about these things. Not in the math. I don't mean in the math. I mean in thinking about these things, the philosophy of these ideas. Last couple of weeks, we asked questions like, what's the probability of seeing R red balls from an urn in which we have this. So we have the probability of R given B. B is, it's a device. It could be an urn. It could be a device that takes red and white states. These states could be labeled success and failures. These states could be on and off. These states could be any kind of a dichotomous thing that we want. In any case, we know, we're assuming we know, we always assume we know whatever's to the right of that bar in logic. That there's m of them that are red, and that there's n total. And that means that there's n minus m that are not red or white or whatever we like. That's one way of writing this notation. Perfectly fine. And I like it myself. It has lots of good uses, and I prefer it because it states very boldly what's going on. This is the probability of this particular proposition, assuming that proposition, which is usually long and complex, is true. Okay. Today, though, we're going to learn I'm going to follow James in this notation. We're going to write it in a functional, or not a functional, a function notation, where we have a function of R given these particular constants. And there's absolutely nothing wrong with this. This is a good shorthand way to keep track of things. I mean, you don't want to write all this out every single time, and it conditions on just what we want to know. This is a tacit way of including all of these things without spelling them all out. And as long as we keep in mind that this shorthand NMR is this, we're not going to make any mistakes. Aha! As long as we keep this in mind, which you can already see that I'm hinting we're not going to keep it in mind, and indeed we're not. Anyway, we proved this. This is given. There's n total possibilities inside our device or bag or whatever you like, and m of them are red, and we've taken out n of these things. It helps to have the notation correct, doesn't it? We've taken out n of them already, and that n will be some combination of whites and reds, or ons and offs, or successes and failures, or whatever we have inside. This is the probability for seeing a particular R, given we have these things. And this is just called the hypergeometric. If you did the homework, you played around with this. I'm not going to prove that homework for us. I think it's rather easy. It's all in Jane's anyway, and we did an example of it in class. So if you don't have it, you just have to keep trying until you get it. It's all there step by step in chapter 3 of Jane, so just follow along. Anyway, there it is. It's no problem. But remember now, this is quite a monumental achievement. What we've done, and we have to remember here, is we have proved, we have deduced all of this. This is a deduction based on very simple premises. We didn't even know probability could be represented by a mathematical function of any kind. Yet we proved it did. We proved that mathematical function turns out to be looking like Bayes' theorem. We can assign numbers to probability. We deduced that. The number 0 turned out to be for falsities, local falsities. The number 1 represented truths, local truths. And with the help of the deduction through the symmetry of individual logical constants, we got to what is called the statistical syllogism. That's one of the first sticking points that people have. Basically assigned equal probability when we know nothing about anything, what's going on inside our particular device, except the number of possibilities. And so we have deduced all this. There's absolutely no problem. There's no paradox that can develop through this. There's no faulty thinking that can arise to this, as long as we keep all of these things in mind. And it's an absolutely useful thing to do. This is, in fact, our first model. If we have a real device, if we have an actual bag, with, I got this bag, this is for Greedy. He was over there, but he won't come up here when I'm talking. Of n total of these kernels in here, some of which have blunt ends and some do not. Well, we could just draw in here and we can calculate the probability of seeing any particular number of these. We could do all that. That's a model for this real world life situation. It's not what goes on in this real world life situation. In this real world life situation, everything has actual values that are under the purview of actual causes, and all sorts of things are really going on, which we have assumed away in our model. Our model is only considering our state of uncertainty given these things and nothing else. And I've already linked several times the coin flip machine that says if we know all the causes of something, why then we know the absolute outcome of those things, and there's no probability indeed. Okay. Now, this math here, I hope you're following this about a model. This model is not the real life. It's a model. You have to come over. Everybody wants to see you. Come up. Okay, he's not going to do it. He's very shy. This math, although it doesn't look that complicated, it's a pain because it involves all these factorials and all this kind of a thing. And these are, they're not the most difficult things in the world to calculate, but it's a lot. And we might be able to find an approximation to this. And if we could find an approximation to this, that would be useful. So let me erase all of this, and we're going to find our first approximation to this. That's all it's going to be, just an approximation to this. And at that point, when we forget that it's an approximation, we're going to be committing our first sin. The first sin of the first deadly sin of reification, I told you, is when we assumed the model was reality. The model is never reality. The model is a model. The model is a state of our uncertainty in things. The model is in our minds. The model is epistemological. The real life is ontological. The real life has its own causes and powers and essences and all this kind of thing. So, but the second one's going to come in making that same mistake yet again. So let me erase all this. I'm following James chapter 3 here again. I'll keep this up right here. So another way to write this particular thing, I'm going to make sure I use his notation. This is I mean, you turn to another book. You go to Wikipedia or something like this. You go to Wikipedia, and they have different notations entirely for the letters and all this kind of stuff. These are just notations. These are just helpful shorthand, so don't get caught up in that so much. All right, I could rewrite this whole thing as 1 over n to the r, m choose r, times 1 over n to the n minus r, n minus m, n minus r, all divided by 1 over n to the n, and choose n. This is the same thing. No problem here. I've only divided. I've multiplied and divided the numerator. That is to say, I've multiplied the numerator and the denominator by the same thing, which is n to the n. So far we have no problems. You got to come up here. You got to come up here. I don't know if you can see him down there. Okay. Yes. Now, so let's just take one of these here for an example. We'll take this right here. We'll call this A, B, and C, these factors right here, so that A equals, make sure I have his notation correctly. Aha. Yes. So remember now, this M choose R equals M factorial over M minus R factorial times R factorial. And that's all we need. We take out this R factorial. We keep this R factorial here. And then we just recognize, well, M divided by M minus R factorial is what? Is M divided by N. You'll see how this is going to go. Minus 1, M minus N, 2N. And then finally M over N minus R minus 1. And all this is just keeping track. I mean, you can go through this carefully. It's just M divided by M minus R. So we must only have M times M minus 1 times M minus 2 times M minus 3 times M minus 4 all the way to M minus R, because we have divided by M minus R. So we have M minus R plus 1. So that's all we have. It's very confusing. I'm probably going too quickly for the math. The math is not the most important here. You can piece this out. So M divided by M minus R is going to be M times M minus 1 times M minus 2, and so on, down to M minus R plus 1. Right? And all then we do is divide this n to the n we have up in here, and that's how we get this thing right here. Now, here's the trick. And I have to erase something, so I'm going to erase this A, B, and C here. I'm not going to do all this. It's all in Jane's, and the whole only point of this is to show you just a simple mathematical trick. So I'm going to erase this and hope you have it. I'll keep the hypergeometric form up there. So basically, we do the same thing for B, and we do the same thing for C. And then we very carefully let N and M go to infinity together. Why infinity? Well, we're going to let this thing go out to infinity and take the limit, is what we're going to do. If you remember your calculus, we're going to take the limit of this thing and see if we can get an approximation. We're going to do the same thing for A, B, and C. Obviously, we do the same thing for the entire hypergeometric function, but it turns out in this case it's all multiplicative, so we could do each one individually. I'm not going to prove all that math. It's not interesting. But it does mean that this thing, A, goes to F over N, where F is going to be our M over N. And the B part goes to 1 minus F to the N minus R over N minus R factorial. And then finally the C part goes to 1 over N factorial, which if you have any calculus left in you, you'll be able to see for yourself quite easily. There's absolutely nothing to it. So the function itself, h, as n goes to infinity, itself goes to the function n choose r, f to the r, 1 minus f to the n minus r. And this is called the binomial. Sometimes called the binomial distribution. This is an approximation to this. This math is very simple compared to this anyway. It's not very difficult math, and it could be very useful in lots of ways for doing other calculations with this kind of a thing when n is large. N large. Okay, so what does that mean? So anything n, capital N greater than about 20, plus or minus, depends on m a little bit. This is an excellent approximation to this. So we could plug this in, use this as an approximation for this, and we're going to be making very small numerical mistakes. Of course, very small depends on the use to which the model is put. I cannot stress that enough either, but if your applications are average or something like this, then you'll be able to use this as an approximation for this, no problem. But when n is less than this, particularly when n is small, less than 10, something like this is a lousy approximation of this, and you're better off using this math up here, which nowadays, with the computers we have and everything, it's nothing. However, this is where the deadly sin of reification arises. All we've done, if we keep in mind that all we've done is just let n and m go to infinity in a nice way, which you understand me, nice uniform way, we can have this approximation. But if we forget that, then we're going to be in some deep kimchi. Because what have we done? We have to really think about this. It's no problem if that's all. I cannot stress this enough. If we keep in mind it's an approximation, we're going to be golden. But if somehow we start with this, we have committed the deadly sin of reification. The deadly sin of reification. Because we got to consider what's going on here. If we said this is the way life really works, and we make the mistake assuming this is the way these models, the model really represents reality, we have done something amazing. This should amaze you. F, sometimes people will write it as P, and it becomes, people will say, the probability of success, or of red rather, of success, or red, or whatever we're going to call those states. No, absolutely not. Absolutely, positively, no. Absolutely not. No. But they'll say it because they have forgotten they've made this approximation. They have committed the deadly sin. The model has become reality. You have said the probability of success. There is no such thing. All we had is a model that we said we know we have n things in there, m of which are in one state, and the rest are in another. It doesn't have to be a bag we're reaching into. It could be anything, absolutely anything, which we're uncertain of. But when you do this, you have, and this is where all the wars come in. And all of a sudden, frequentists will start arguing one way about this thing called, now it's called a parameter. And usually we write parameters in Greek letters, but for historical reasons, not so much for the binomial. I will write that parameter as theta. I do in my uncertainty book. James keeps it as f, whatever. It's just notation, but the notation writing it in Greek letters helps us to remind us it doesn't exist. It doesn't exist. This parameter does not exist. It doesn't have an observable value. And I say this quite adamantly. We cannot observe this value. And so that we get into all these wars between frequentists and subjective Bayesians. Subjective Bayesians, now let's say that you have to have, we haven't talked about all this stuff. We're going to get all this, but they're going to put prior distributions on this. And it's terrible because they think they can subjectively assign probabilities to every possible value of theta. So let's think about what every possible value of theta is in this approximation, or f. It's all the same. F, you'll see it written all kind of different ways in every different textbook. You always gotta be aware of that. There is no such thing. It doesn't exist. This is a mathematical approximation to this model. Okay? This is a model then of real life. We have two layers of models of real life. And so we got to be careful we don't commit the deadly sin of reification twice. This only states our uncertainty in something, not the way things really are. All right, so let's talk about infinity. Now you've seen, I'm going to leave this up. I'm going to, well, I guess I don't need this over here. I'll just do this. You've seen notation like this, 10 squared equals 100, and then 10 to 3 equals 1,000, and so forth. There's another thing called a tetration. It's the same thing, but we want to write big numbers. We want to write big numbers in a compact way. Of course, I can write 1,000. 1,000 may not be big. I can write a billion by going 10 to the ninth and so forth. That's a sort of compact way. However, if I want to talk about really big numbers, really big numbers, I need to use better notation because that's going to get bothersome. So we're going to write something called a tetration. So we're going to write there's lots of ways to do this. There's a Donald Knuth's up arrow notation. We'll come to all this maybe when we talk about infinity again. We're going to talk about infinity a lot of times. It's a good pun. This is 10 to the 10 to the 10. I am taking whatever this number is and I am raising it to the power of itself 2 times. 2 times. So the tetration of 10, 2 tetrating 10 is 10 to the 10 to the 10. And that equals, well, 10 to the 10 is 10 to the, make sure I get my number of zeros right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I got that right. 210 is a close way of writing this. I mean, is a compact way of writing this big number right there. Okay? I can go to town with all these kind of things. I can have 2 to the 10, that same tetration, and I'll make that the tetration of 10. So that is 10 to the 10 to the 10 to the 10 to the 10 this many times. Now that's a very big number. That's an enormously large number. And if we keep that number, whatever that is, that's going to be our n. This is going to be n. N is going to equal for now just this particular number right here. And m will be some number less than or equal to n, and they're both greater than 0. I can calculate this number, in theory anyway, mathematically. On a computer, maybe that's a different problem altogether. But I can calculate this number. There's no difficulties with it. I'll run into no complication. I will run into absolutely no paradoxes. I'm not going to run into any of this discord between frequentism and Bayesianism and all this kind of nonsense. I don't need it because my number is finite. All right? My number is absolutely finite right here. It's a very large number, but it's still finite. And therefore, I can get the exact probabilities from this calculation. I cannot stress this highly enough. I cannot stress this high enough. We're in weird territory right here. Okay? And I could go further. I could take this. I'm going to get rid of this Deadly Sin of Reification stuff up here. And I'm going to get rid of these tetrations. I can let n be, oops, not NO. No. I can let n equal, I mean, you can just go wild with this stuff. You can do a billion, a tetrating 10, tetrating a billion, tetrating a billion, tetrating 10. Now, I don't even know what to call that number. It's a very large number. However, it is still infinitely far away from infinity. I hope you agree. Now, however many m are in there, whatever. They could be some other number. It is still going to be the case if we take some parameter of m divided by n. It's still intelligible. It's still intelligible. I know I can think about assigning probabilities to every possible value of f or something like this. If I'm a Bayesian or a frequentist, if you've seen all these kind of things, that statement will make sense. If you haven't, that statement won't make sense yet. But the whole thing is still finite. I have made absolutely nothing. I can still keep within the strict domains of logic. But the minute I let these things go to, both of them go to the limit, when I shoot them off at infinity, when they get to this mysterious place of infinity, all of a sudden everything's out the window. How can I assign probabilities to our uncertainty of this f parameter? All right, we're going to go through this again and again and again. How can I possibly do this? How can I have the temerity to say, I know what everything's going to be in this very simple counting infinity? It just boggles the mind. This kind of number you can't comprehend. I can write it down like this. I could I can make even bigger numbers. There's other notation for numbers bigger still that are all going to be infinitely far away from an infinity, but they're still just counting infinities. And that's before we reach even the continuum. The continuum is even more bizarre. It's an infinity infinitely larger than the counting infinity. And most of the math that's done on us, all this calculus stuff that's done with probability, is done with the math of the continuum, which is incomprehensibly larger than this counting infinity, which is already too big to think about. So how can we sit here and think, I'm going to assign subjectively probabilities to every possible number? No, absolutely no. We've seen here our first hint. We're going to come back to this. This is still not satisfying. This is James's first attempt at showing how the binomial comes about. I don't think it's satisfying because it does say we know exactly that there's m in there, and that there's n total. There's m in the success state or the red state or something like this. Ordinarily, in a lot of problems, we don't know exactly what's going on. We don't know even how many. All we know that there could be a success or failure. We don't know how many. And we don't necessarily even know how many there are going to be, how many n, and so forth. So if we do that kind of thing, that's Laplace. I have my book over here somewhere. Laplace first did this derivation. That's a more satisfying way of reaching the binomial because we get there either way. We get there either way, but it's a more satisfying way of thinking of it. And as long as we keep in mind all of these things are only models or approximations to real finite discrete things, which is only we could ever measure finite discrete things. Space itself may be continuous, it may not be. There's arguments either way. We won't get into all that kind of stuff like this today, but as long as we keep in mind what's going on with the math we're using, and we don't let ourselves be fooled into thinking this suddenly has existence just because we took the limit, we're going to be okay. But when we forget that we started with these very simple deductions, and all we're trying to do is find a good approximation to this, which is already just a model, then we're going to be in a world of hurt. We're going to go over and over that again. It's only a kind of a rough sketch, and a lot of it won't make sense to you because I haven't done all of the introductory material on what formal probability models really look like and so forth, except for this one. All right, so the homework I'm going to put down in the comments there. It's basically just another exercise of the hypergeometric. The next week, we have to get back into the philosophy of stuff. We have to start talking about what probability is not. We already did what probability is. It's logic. It's just logical deductions. As long as we stay in the realm of logical deductions, even when we're doing this limit to infinity, we're absolutely golden. We're not going to make any mistakes. But there's lots of mistakes that can be made. So we're going to go over probably at least a couple of weeks the mistakes that are made and thinking about probability. So we're going to learn what probability is not starting next time. All right, so the written lecture will be down, found at the links below. And if you have any questions, put them in the comments and we'll get to them next week. That's it for now. Thanks for listening.